Hi, it's me, Tim Dodd, the Everyday Astronaut. Welcome to Cape Canaveral, Florida. I'm here at Blue Origin's factory, and I'm going to do a world first with you. I'm going to take you inside their incredible factory. We're going to see their next vehicle, New Glenn, which is one of the largest rockets ever made. And we're going to see inside of the rocket. We're going to see the landing legs. We're going to see the interstages, the main tanks, the engines, the fairings. We're going to see everything as it's being assembled for its first launch ever. And stick around for part 2, where I'm going to take you guys out to the launch pad, where you're going to see where New Glenn's going to be launching from. It's incredible. And best of all, we've got a pretty great tour guide, Jeff Bezos. Let's get started.
Hello.
Hey, how you doing, Jeff?
I'm doing all right.
Hey, I'm Tim.
Jeff.
It's so nice to meet you.
Welcome to Blue.
Thank you. What a grand entrance too here.
Oh yeah, brings back incredible memories. Yeah,
Oh,
of course.
I'm sure. Remind me, this is the first one you guys landed, if I recall,
that's
right?
That's exactly right.
Yep.
Yeah. But I think this one's flown 5 times, 6 times. I can't remember.
Yeah,
But,
it was a handful of times, which is
that's right.
crazy, and now it's just a lobby decoration.
Yeah. Yeah, and of course it fits easily inside of New Glenn's fairing. So
That's the craziest thing about it. That's insane to think about, because I don't think people understand the scale, even though this is a relatively small rocket. I mean, it's still huge.
Yeah, that's
it's still huge. And we're, 4 stories here? Yeah.
It's a very, like the ring fin, even there are a lot, this is, it's a very clever design. This vehicle is very unusual because it has to fly in 2 directions.
Yeah.
It flies up and it flies down, and it has to be aerodynamically stable with both ways. And so that ring fin is a clever part of that because it's shielded on the way up by the crew capsule.
Yeah.
And when the crew capsule separates, that ring fin becomes a descent-only aerodynamic feature.
Yeah.
So.
And then also you have the pop-up fins at the top of the ring that pop out.
That's for additional reentry stabilization. Then there also are drag brakes that basically are there to increase to make the ballistic coefficient better for the propulsive landing.
Right.
So it makes our terminal velocity much lower.
Yeah. And you also
and then this is for steering.
Yeah.
So you go up, and we do something very unusual. On the way up, we measure using just inertial navigation, and so we can measure the high altitude winds just by how we know how we're steering the vehicle.
Yeah.
And we know where the vehicle's actually going, and so we can impute the high altitude winds. And then we adjust for those on ascent so that when we come back down, the high altitude winds will blow us directly over the landing pad.
No way.
And that corrects most of the error. But then the remaining error gets corrected by these fins so that we can fly over the landing pad.
Yeah.
And then the final error gets corrected by the terminal descent maneuver. So anyway, there's a lot going on. The fact that something like this lands propulsively proves that math works.
Yeah.
Do you want to go in?
I do, but I have to check out. I try to save it because I saw it over here, and I see the words X33, and I have to have you show me what this.
There are so many objects. I don't know if you've ever been to our Kent facility.
It's been about 5 years, but I have been out there.
Yeah. Well, as you can tell, this is one of their umbilical panels, and so it's just we have objects like this all over Blue Origin. It's kind of inspiring just to see what others did, and how they made things. If you ever look at some of the, a lot of the. A lot of rocketry was figured out in the 60s.
Right.
We've improved manufacturing techniques. We've improved sensors and computation. They wouldn't even recognize what we can do with flight computers and sensors, and so they'd be blown away by that.
Yeah.
But the big things about rocketry, regenerative cooling, common bulkheads, all these things they invented are, they haven't really changed. They haven't changed. So our job today is not to do better than they did at spaceflight, It's to make it more affordable. So, spaceflight has been a solved problem for a long time.
Right.
The thing that's not solved is making it low cost.
Right.
And,
Interesting.
That's about reusability and manufacturing techniques and other things.
Yeah. It's just, I mean, it just,
I know you're a buff.
Yeah, exactly.
You're a space buff.
When I walk in and see a X-33 umbilical fin, I'm like, okay, this is cool. This is really cool.
Well, sometime you'll have to get a tour of our Kent headquarters too, and you'll see there's lots of cool artifacts around from the old days.
Yeah.
I think I recognize those.
I think you of all people would recognize.
I think I pulled one of these up off the bottom of the Atlantic Ocean. Actually,
that is the craziest thing anyone can say. Genuinely,
it's in the Smithsonian now.
Yes.
And so it's an Apollo 11 F1 engine. I was sitting in my living room one day, and I said, I wonder if you could find those F1 engines from Apollo 11 sitting on the bottom of the Atlantic somewhere. And I went to Google, and I typed in Apollo 11 booster impact coordinates. Yep. And they popped up. They had radar tracked it all the way to impact.
Right.
And so I thought, this is going to be the easiest thing I've ever done. I'm going to go recover those engines. Of course, that was the only part of it that was easy. It turned out to be incredibly hard. We did side scanning sonar first, and the problem is we located too many objects.
Really?
So it's like NASA's graveyard out there.
Yeah.
Like, all this stuff that flew out there, most of it, there's like a big 30-mile long ellipse.
There, yeah.
Very similar corridor. And so we found some things that we thought were very likely, and then we had to go investigate them. So we put together a big mission with remotely operated vehicles with like high-def cameras, and it's in 14,000 feet of water, 7,000 PSI, so everything you do in those environments is very difficult. But it was actually incredibly fun. I brought my mom and my dad and my brother and my brother-in-law and my mom. There was 60 people on the boat where we recovered the engines. And there were 59 men and 1 woman, my mom.
That's awesome.
So anyway, it took a full month. We were out at sea for for like 28 days, and pulled up those engines. And that Apollo 11 F1 engine that actually flew the men to the moon is literally in the Smithsonian as a result of that. That is the
coolest. And when that's stuff that I don't think people even appreciate. Like I barely know that story, and I
don't think many people know that story.
I mean, you literally went.
You should go to the Smithsonian and see it. It's an incredible artifact.
Did you used to have it at the Air and Space in Seattle?
I also pulled up a second engine. It turns out to be from Apollo 13. That one is in Seattle. Oh. So the Apollo 11 one is in the Smithsonian, and it just went on display about a year ago. They've been refurbishing the Air and Space Museum. Yes. And so it's there now. It's part of the permanent collection now. It's really cool. And it's next to, they've done a really nice job because they've set it up next to an unflown F1. So cool. You can see, the actual article and an unflown one in pristine condition. Cool. Because of course, after many decades on the bottom of the ocean, it's eroded.
Yes.
And, it impacted the ocean at high speed.
Right.
And got crushed.
Yes,
and there's all kind of the bell of the nozzle is very fragile.
Right.
So it's
paper
thin.
Tubes,
I mean, it's these tiny little tubes all brazed together. I mean, it's a work of art, by the way.
It is. Yeah.
Anyway, you want to go inside?
We better see what you guys are looking at. Yeah. That is so cool.
It's fun to pick up engines off the bottom of the Atlantic, but it's even more fun to build rockets.
To build them, yeah.
Yeah.
Well, I don't think too many people can say that either. Like, yeah, what'd you do on holiday? Went out and grabbed some engines that took us to the moon.
All right.
Okay.
So I'm going to take you on a little tour, and feel free to ask questions along the way. Let's go. Okay. We'll start down here, and I'll show you how we make the tanks.
Okay.
And then we'll just wander around.
Oh. Hey, I gotta just scope this already.
We'll come back here too.
We'll come back, okay.
But feel free.
Oh, it's huge.
Yeah,
you see pictures, and
it's hard to tell. The scale of things in person is always surprising.
Yeah.
And the first time you see a flight article or a development article, it's always surprising. You see it in CAD, and it always looks the same size. It's always the size of your computer screen.
Exactly. And I think people just, even when you see a picture of like a factory floor, you don't have a normal scale of reference to the size of the factory even.
No.
So your eyes just don't quite click on how big things truly are. When you say it's 7 meters in diameter, what's that? that doesn't translate, you know?
We can go this way. We'll walk. We'll do the narrow path. This is where we make the tanks.
Okay.
And that probably obvious from casual inspection, but watch these little things.
Yep.
Wow. You can see inside here, you can see the orthogrid.
Yep. Jeez.
This is a GS1, Glenn Stage 1, the booster stage. This is an LNG tank.
Okay.
For the booster.
Okay.
And actually, this outlet that you see here this is the common dome. So this dome separates the LNG from the LOX.
Yep.
This is the downcomer.
Okay.
So the LNG comes down through the LOX tank.
Yep.
So what's about to happen is that the first barrel section of the LOX tank is about to be friction stir welded onto this. So the common dome just got, we just finished friction stir welding that in. That's the friction stir welding head over there. Wow. This rotates at a certain rate. You develop weld schedules and so on. And the domes are the inner part where you see the isogrid. That is spun formed, and then these gore panels are friction stir welded on to increase the diameter of the dome. So anyway, this is a very high performance way to build a tank, and especially because it's a reusable vehicle, you get to reuse all of that high performance.
Right.
You're not building this incredibly high performing thing and then throwing it
away to be recovered on the ocean by someone 50 years later.
Exactly. Perfect.
Well, that's what's so cool. I mean, you can tell just you guys are obviously, this is at a very finished standpoint. Even what the downcomers put into looks like a piece of art. It's
a good aerospace hardware does look like art. Because it's so, you're just going for function.
Right.
But there's something about when you go for that last 1% of function, it really makes things beautiful.
Yeah, the geometry is kind of...
Yes, highly engineered objects always end up looking beautiful.
Yeah. Oh, that's really cool. That's really cool. And so that's going to be friction stir welded onto the top of the LOX
so this is
tank here.
you can see they're rigging this. You can see it's getting rigged right now to be lifted up. It'll be moved over here, and then it gets, pressed up against this.
Yep.
We'll trim it to get the fit exactly right, make sure they're completely parallel. And then once they're trimmed and in location, clamped together, then that friction stir welding head will do its thing.
Yep.
And then it'll be, NDT inspected to make sure that weld is good, and then it goes on to the next step.
And then you just keep adding the rings.
You just keep adding barrel sections.
Okay.
And so the barrel section, here, we can walk over there. The barrel sections are made over here. So this is where the vertical welds are done. We have 2 of these stations. There's one down there too.
Okay.
But these are where the vertical welds are done. So each of these panels is made. We'll go in the next room and I can show you where the panels are made. But each of these panels are milled and then bump formed, and then they're welded together vertically like this, and then they're attached to each other horizontally over here.
Okay. So I know there's kind of the iso grid on the inside of the top of this.
Technically, that's orthogrid.
Orthogrid,
The isogrid is the one that is triangles.
Right.
And orthogrid is rectangles.
Orthogrid,
and the orthogrid is way better if you can get away with it, because the orthogrid is easier to mill, much cheaper, and also you can bump form orthogrid. You can. I'll show you I can show you in the other room. Isogrid, you really have to mill it with like a 5-axis machine after it's already been formed.
Okay.
You can't really bump form isogrid.
Right, yeah.
Now, but the advantage of isogrid is it's very high performing, especially if you're taking loads in every direction.
In all directions. Yeah, makes sense. This is a huge building in general too. Like
this is a huge building.
This is massive. If you see it from the road when you're going to like the visitor center and stuff, which is actually really cool when you're.
It's really
when
cool.
the public can just drive right by.
We're like
and see
right
it.
next to the visitor center. I love it.
Yeah, but then when you're inside it, it's another thing altogether.
This is where where we weld on the gore panels to the spun dome.
Oh, okay.
You can see it happening here too.
Yep. Wow.
All these little, by the way, all these little markers.
Yep.
Lets you do metrology. So you can use the machine vision it just looks at this, and because it has all these little markers on it, it can look at you can use machine vision technology to look at these parts and just make sure they're right.
So it's like a QR code for every piece?
I mean, they're not, by the way, these are not put on carefully. You can put these stickers everywhere. You don't have to put them on very, very carefully. You can just put them anywhere. In fact, you're counting on some randomization so that the machine vision can look at it.
Oh, and it just catalogs it at the beginning.
It just looks at it, and it knows whether, it can see where each of those dots is, and then it can just tell you every one of those dots. You can go look at the CAD, and you can see, is this dot, does it match what the CAD says it should be?
Wait, so are they just physically put on like...
They're stickers. They're decals.
Literally...
They're little tiny decals.
No.
And it doesn't matter where you put them.
Do those have to be removed before flight?
Not necessarily.
For
it depends on what the next processing step is. In our case, we're putting thermal protection over this.
Right.
It's kind of, I don't know if we remove them or not, actually. We can find out.
For some reason, the idea of just throwing stickers.
Isn't that cool?
It's just random and cool.
It's such a clever way to do it. All right, I'm going to give you a real treat now. We're going to go up. I'm going to let you look inside of a hydrogen tank.
Oh, yes.
So this is a GS2 second stage.
Okay.
This is a GS2 hydrogen tank.
Okay.
And so we're going to go up these stairs, and what we're doing right now is we're installing the helium bottles inside the hydrogen tank.
Cool.
So you can come look.
Oh, awesome.
We might have to put some bunny suits on.
Okay.
Hey guys. So we've got a little airlock here, clean room. We want to keep the inside of the tank clean. We're just we'll put a little suit on. We'll be able to go inside the airlock, and then you can poke your head in.
Cool.
And what you'll see in there is you'll see the whole tank. A lot of it is covered up in plastic, but you'll still be able to see. And then and you'll see the cryo helium bottles.
Cool. Yeah. I think this is only the second or third time I've ever actually put on a full bunny suit.
If you want to take a seat, that might make it easier.
Oh, I think I'm already in.
You're good.
I'm a pro for those
like,
for those previous experiences.
Very coordinated over there, Tim. Okay. Not many people have seen inside a big LH2 tank.
I know, and it's a big one when you think about it.
It is.
The only LH2 tank that has ever been bigger is the S2B on the Saturn V.
That's right. And it doesn't go to space.
Right.
It doesn't go into orbit.
Into orbit. Yeah. So yeah, and even when you think about the S4B, that's only, what was that, 6? That might have been 7 meters in diameter, but this is a much larger stage than the S4B though.
Yes. All right.
So, as we walk in,
Do you want to?
Yeah, I'll make sure. Just step on the mat.
Okay.
Couple times, and you're gonna walk in.
Thank you.
Here. Holy crap.
Watch your eyes.
It'll be bright? All right, it'll be bright. I'll look away from the light. Oh, that is sick.
Kind of have to, this light,
Yeah.
you kind of have to eclipse it.
Yeah, you do.
I think I might have a better view over here. Come
Oh,
over
okay,
here.
okay.
Up on the upper left.
Oh, right.
Do you see the helium bottles?
Yeah. Oh, that's
Want me to
awesome.
kind of,
Yep, we got
you
it.
got it?
Yep. That is, so you got 4 there, 2 more down here on the bottom.
Yeah, and
bottom
I mean, basically, they don't go all the way around, but there's a number of them still to be installed.
And so they just climb down the ladder there.
And you can
walk.
see the orthogrid.
That is awesome. And so is this the top here then?
This is yes, and that is and then below here would be the aux tank.
Okay. So when it's ascending at least, well, I guess as it's under acceleration, the liquid, the bottles will stay as much in the liquid propellant as possible.
Correct. Oh yeah, I think that's better.
Wow.
That's a little better.
So we got the whole bulkhead here that we're poking our head into. And then on top of this will be all the fairing adapter and the payload adapter will sit on top of, basically on top of this right here.
Exactly.
And then will slosh baffles, do they have to be
Yes,
built
there
into
are
here too?
There are some baffles too. I'm not sure. But you have to remember the ISO grid does a lot of that job for you.
Mm-hmm.
So the baffles are actually more important on the LOX side because the LOX is so much denser.
Oh, right.
But remember, LH2 liquid hydrogen is so
Sparse,
light
or whatever, yeah.
Dude, so a cubic foot of liquid hydrogen only weighs 4.4 pounds.
Oh my gosh,
A cubic foot of liquid hydrogen only weighs 4.4 pounds.
That's crazy.
So, a cubic foot of water or LOX probably weighs 60 plus pounds.
Right.
So,
Wow.
you pick up a big bucket,
Right.
picture a bucket that's like a cubic foot size bucket.
Right.
It's heavy.
It's heavy, yeah.
And, you pick up a bucket full of liquid hydrogen of the same size, it's incredibly light.
That's crazy.
And so
to think about.
slosh with liquid hydrogen is not a major issue.
Yeah, it doesn't have as much.
You worry about other things, like you don't want, you worry about utilization. So if you need to make sure that your, where you're, the sump, where you're collecting the last bit of liquid hydrogen, you don't want slosh down there,
Right.
Because you
might start
suck a
ingesting.
bubble,
Yeah.
and so which would you wouldn't be able to get good utilization if
Right.
you had that issue.
Yeah.
So you do have to design certain features to make sure you can get great utilization.
Yep.
But typically with LH2, slosh is not an issue.
That's crazy. Wow.
Thank you. I really
Yeah.
appreciate it.
Yeah,
Right?
thank you. It's awesome.
That's-
That's great.
That's
Super cool.
that's a good ride right there. Thank you.
You guys have a good one.
Thank you.
We can keep heading this way.
Cool. And I'm already seeing the aft end of your second stage, right?
That's right. So this is actually the flight article.
Oh.
This is the second stage that will take Escapade to space a little later this year.
No way. That is awesome. So that's your first orbital second stage right there.
That's it.
That's it.
And in fact, the flight engines are in this building. I'll show them to you a little bit later.
Yes.
Because you saw as you came in. That's the flight article for the aft section of GS1. So that's the aft section of the booster.
Wow.
The engines get mounted. 7 BE4 engines get mounted in the base.
Jeez. Oh, that's the inner stage there, right?
This is the forward section of GS1. So on top of
Sorry,
that,
the GS, your
forward section of GS1 of the booster.
booster. Okay.
So basically, that's the bottom of the booster.
Yep.
That's the top
Yep.
of the booster.
in your
and
interstate
in between
kind
is basically the big tank, the big
Yeah.
GS1 tank. And
Yep.
I'll show you the flight article of that too. It's in a different building.
Okay, cool.
But
These are flight articles.
These are
here,
flight
though?
articles. These are Mission 1 flight articles.
Wow.
And what you see, that the fabric covering is our thermal insulation.
Oh,
so we
cool.
developed that ourselves, and it's highly reusable. It's been tested on New Shepard. This vehicle comes in at Mach 6. It goes through some quite extreme heating environments. We have developed painstakingly a very capable, reusable thermal protection system that doesn't need to be touched up. So
Wow.
we're really excited about that. It's part of that path to reusability. Not just reusability, but operable reusability.
Right.
It's through low inspection, fast turnaround. This vehicle is designed to be turned around in 16 days.
Really?
16 days.
Oh my gosh. That would be game changing.
That's the design.
Wow.
And designed to last for a minimum of 25 missions.
Wow.
So I'm hoping it will eventually be much more. We'd like to get to at least 100, but starting with a design for 25. So,
Wow.
We can
So
go.
so that finish is what we're gonna see. Like that's, or does it get painted over that?
It'll be painted, but that is the actual material. That's the thermal material. So they're doing hydraulic testing right now, so we can't get too close. But we can still look at things pretty well from here. You see the landing gear. There are 6 landing gear,
Yep.
and you can see the landing gear doors. The landing gear deploy starting 14 seconds from landing. They deploy. It takes them 8 seconds to deploy.
Okay.
So they're fully deployed 6 seconds before landing.
Okay.
The deployment is gravity assisted because you're decelerating.
Yep.
So you've got good gravity assist on the gear deployment. There's a lot of effort that goes into making landing gear lightweight. It's parasitic mass relative
Right.
to an expendable vehicle.
Yep.
So we've learned a lot about this from New Shepard, and we're able to take those lessons and put it in here. So the 6 landing gear, between about 4 and 6 landing gear, your mass trade is kind of even. When you have more landing gear, your splay can be smaller to get the same tip over.
Yep.
So if you're designing for a certain probability of tip over, and if you have, let's say take the extreme case, you have 3 landing gear, then they need to get the same probability of tip over. You need to have very big landing gear.
Yeah.
They have very wide splay.
Yep.
If you have 4, they can come in a little.
Yep.
If you have 5, they can come in a little more.
More.
If you have 6, they can come in a little more.
Interesting.
So you're trading that. In our case, we like 6 because geometrically it fits really well with a 7-engine configuration.
Yes. Yep.
So you've got a landing gear between every
Between
engine.
engines. Yep.
You've
So
got the
put-
center engine, and you've got a ring of 6.
Yep.
And it just packages
That
well.
makes complete sense.
Anyway, the aft section is really interesting. So the engines fit up inside there, and then there's a heat shield where each engine has its own eyeball seal. Same technique we use on New Shepard.
Yep. And now when the legs are going to be fully deployed at about 6 seconds before landing, are we expecting to see New Glenn kind of hover in a similar manner to
Yes.
New Shepard?
Yes.
And then kind of hone it in at the last second?
We can do sustained thrust to weight equals 1.
Okay.
So the engines they can throttle. The BE4 engine can throttle down to 40%.
Yep.
And so the final landing maneuver can be done at at constant descent velocity, which
Right.
is what New Shepard does.
Yes. And then if you think about it in the total throttle scheme, if you have 7, you're already dividing by 7, and then 40% of
Exactly.
that. So you're really
So
down to like.
So there are 3 gimbling engines on this
Oh.
vehicle, and 4 fixed engines that don't gimbal.
Interesting.
So there's a line of 3 engines.
Yep.
For the return, we light the 3 gimbling engines to
Yep.
do the full deceleration.
Okay.
And then we do the final landing on a single engine.
Okay. Cool. So
The vehicle, as you know, with this is so light. It starts out very
Right.
heavy.
Yes.
Because it's got, millions of pounds of fuel and oxidizer on board.
Right. It's really heavy.
It's really heavy. By the time you land, it's really light.
Yeah.
And so, the dry mass of this whole vehicle is only a few 100,000 pounds.
Right.
You've already gotten rid of the payload.
Yep.
You've gotten rid of the second stage, and you've gotten rid of all the fuel.
Yeah.
So you actually have a very light vehicle that needs to land. And actually, it's, so you need to go down to just a single engine.
Yep.
And then throttle that engine to get to thrust to weight equals 1. But it gives you a lot of control authority on the landing.
Right. And are you doing you're doing always a downstage landing? You're going to be landing
We're going to always land on a floating platform downrange. We're not doing any return to launch site.
Yep.
We might do that later, but it's a very big performance penalty.
Yeah.
And if you are, but it's still a smart thing to do if you have a particular mission that doesn't need the performance.
Yeah.
And so initially we're not going to do that. We're going to do all of our missions downrange on a floating platform, but maybe we will do later. We may do some missions with return to launch site if it makes economic sense.
Right. Do you have to do an entry burn as your?
We do an exo-atmospheric deceleration burn.
Okay.
And then we do a final
landing burn.
Yeah. The exo-atmospheric deceleration burn is actually very short, and we have big strakes on our vehicle.
Yeah.
And so the vehicle's ballistic coefficient is such that, including the strakes, allows us to be very fuel efficient. Mm-hmm. And so we kept doing these trades, and the strakes always wanted to be bigger.
Oh, yeah.
Because the landing propellant is so heavy.
Right.
And so anything you can do to reduce that length of that exo-atmospheric burn turns out to be a winner.
To win out.
To a point.
Right.
And then at a certain point, you reach an optimum.
Right.
And so you'll see one of the strakes later on the mid stage, on the mid module. But anyway, it's a very cool design. We're close. We need to understand our heating environments better, which we'll start to do after the first flight.
Yep.
We want to learn whatever you can learn on the ground through simulation and ground test. You want to learn, but there are some things you can only learn in flight.
Right.
And the final environments is one of those things.
Yeah.
So in the beginning, you have to estimate your flight environments, noise, heating entry rates, et cetera, et cetera. You can do a pretty good job with simulation. Today, you couldn't do that in the 60s.
Right.
So there are some things that have gotten better.
Yeah, 100%.
CFD is one of them.
Yes, jeez. Monte Carlo.
Oh, everything. Anything that involves computation has gotten way better.
Yeah.
So you can do a very good job, but you have air bounds. You basically have to design the vehicle for the conservative side of those air bounds. And then once you fly, you can go tighten up.
And you kind of know.
You can anchor your models,
Yep.
tighten things back up.
Yeah.
And so we'll be able to see after the first flight
where you came in at, kind of.
And how long does that exo-atmospheric burn have to be? Cool. Does it even have to happen? Cool. Can we change the thermal protection system a little to get rid of it altogether? Because it will always be a performance improvement to get rid of that burn.
Right.
If you can.
That's cool.
Let's see. Let's keep walking.
Yeah.
Take you over to the forward.
The one's completely cantered. It can swivel 90 degrees if it needs to?
The
fin?
The
or is that just
operating range is 60 degrees.
60 degrees. Okay, so that's just probably insulation there or something?
Yeah. The operating is 60 degrees.
Which is a lot for a control
by the way,
surface.
And these fins move fast.
Really?
These are the largest hydraulic actuators on a space aerosurface, probably, I think, ever. They're 5 times bigger. I'll show them to you when we get inside. They're 5 times bigger than the actuators used on the shuttle SRB thrust vector control system.
Really?
Yeah, they're giant. Well, because you really want to you need a lot of torque because you want to be able to move them very quickly.
Yeah.
These fins book.
And you don't want the aerodynamic forces to be moving, though, they're going to be reacting against those fins. The last thing you want is for those to torque one out of alignment. Oh, this is awesome.
We'll keep going up. I can point a few things out for you if you want.
Holy crap.
So, flight computers.
Yep. Oh.
Everything is one fault operative on New Glenn.
Okay.
So we have
So you have some redundancy.
redundancy. So the big fins. That's the pivot point.
Wow.
So that's the torque box. This is the pivot point.
Wow.
We come up a little further. Here's another. So now we're up above. That's the pivot point down there. That's the hydraulic actuator
Jeez.
that rotates the
steers
fin.
the fin.
That steers the fin.
Wow.
Isn't that incredible?
That's insane.
That's
big.
It's really big.
Wow.
And so there are 4 of those.
4 of them, yeah. That is crazy. And these are our nitrogen or hydrogen bottles there for pressure and probably for RCS and
That's exactly right. These are nitrogen bottles. These are nitrogen pressurant bottles. So, where we're standing, this is RCS.
oh, cool.
Okay, where we're standing above us will be the second stage.
Second stage.
And this space is mostly hollow because the giant space nozzles for the BE3U engines fit in here.
Fit right there. That is crazy. Wow. It
isn't
gives
that
you a sense of the
amazing?
scale of
Yeah.
when we're standing here and yet the nozzle is going to be,
Yes, basically the engines are right here.
yeah. Yeah, the
And
heart of
so-
the engine's right here and the nozzle's going to
That's
sit
right.
right down there.
And these, you'll see
oh, the
all
interstate
of these.
push rods?
Those are the pushers. Very
Wow. They're so big.
good. Yeah. And so where this green, you see this green tooling up here? That, of course, is just tooling. That gets the second stage gets mounted where that is.
Okay. Yep. And then these are, looks like some.
These are this is all part of the RCS system, and so you have to. These are heaters to keep the RCS propellant at the right temperature.
Yep. Get that gas up to operating pressure. Wow. And so you have a quad thruster pack. It looks like 1, 2, 3,
Exactly.
4. Wow. These are just huge. And
The scale of everything is very large.
and so there's going to be, I have to take a look at this now that we're on the inside. So we got a tandem pair here.
Yeah, and
then
they're all the same. It's just not. There's some of them are just not quite installed.
Got it. Wow. So this thing's going to have a ton of control authority with
Yes.
Thrusters
And
galore.
That helps for even for terminal landing.
Right.
The RCS system can
target.
help the position. So you're basically getting to push. You've got thrust vector control at the base to control the base of the vehicle.
Yep.
But you can also control the top of the vehicle.
Yeah. Helps
with-
you be able to do
with your RCS
kind of lateral movement
correct.
like that.
Correct. It's like if you think about it, doing a vertical landing is an inverted pendulum problem. So you're balancing a pencil or a broomstick,
right.
on the end of your finger. And actually, this is one rockets love to be big in a bunch of ways. There's a lot of advantages. One big disadvantage to a large rocket is manufacturing is difficult.
Right.
But there are a lot of advantages to a large rocket. Parasitic mass doesn't matter as much. Rotating machines like to be big because they have parasitic losses too.
Right.
A lot of advantages. Vertical landing likes big rockets because it's easier to balance
On a longer.
a broomstick. You can balance on the tip of your finger. Try doing that with a pencil or a toothpick.
Right.
You can't do it. And the reason is that the inertia slows everything down. So it's much easier with something that has high inertia to balance it.
Yep.
But if you can use your RCS system at the top of the vehicle, the easiest thing to do, you can't quite do this with a rocket, but if you imagine trying to balance that pencil length of your finger. If you could also hold it from the top,
right. You're cheating at that point.
the problem gets a little simpler.
Even simpler.
So to some degree, you can do that. And of course, what you're really trying to do is you do need quite a bit of control authority for that terminal landing, because you don't know what wind gusts you're going to get.
Right.
You get a lot of disturbances.
You need to react to
You
some
need to
of
be able to
those
react quickly
conditions.
to unpredictable disturbances. This is why landing on the moon, in some ways, is actually easier. It's much harder in other ways. For
Right.
example, you don't have a prepared landing field. You have craters and boulders and things that, it's an unprepared
Surface.
landing surface. That makes it harder. But the fact that you have no aerodynamic disturbances makes it easier.
Especially with modeling. You can just say,
Yes, correct. Well,
Yep.
the hard parts, there's still hard parts to model on a lunar landing. We don't know. It's very hard to model the crater that you dig with your own propulsion system and things like that.
Yeah.
So it's a very difficult problem, but it's a different
problem. Yeah. Cool. Yeah.
Can't think what else to show you up here. I guess that's it. You want to head back down?
Sure. Yeah,
I still have a lot to show you.
Don't have to tell me twice. This is awesome.
Look at this is an umbilical panel.
Oh, right.
And this is the actuator that opens the door. Opens and closes the door. So you basically want, this is a T0 umbilical, so when you lift off, the door closes.
Oh, cool.
To protect these so that they'll be ready for reuse.
I'm ready for the next one.
Another thing you wouldn't have to worry about if the vehicle is expendable.
Yeah. That is cool. It's like Willy Wonka's chocolate factory in here. It's like one room after another of magical surprises.
I'm excited to show you the composite bay. This is where we build the fairings and the payload adapter. And it's such an incredible technology. But first, let's look at some large machine tools. And I can show you, you've seen the barrel sections.
Yep.
Now I'm going to show you where the panels are made.
Yep.
Okay.
CNC'd into those
orthogrid.
orthogrid. Thank
Correct.
you. Yep.
Oh, thank you.
Yeah. Awesome. Thank you. How you doing?
Hey, how's it going?
Doing all right? How are you?
Good, thank you. So, this is the finished product. The way this works is you mill this orthogrid pattern while the plate is flat.
Okay.
And then that giant machine over there is called a bump forming machine.
Okay. Yep.
And you basically, after you've milled it, you put it in that machine, and there's a big hydraulic press that bumps it. And as you bump it, it curves. It rolls like this. And so you end up with this final shape.
Wow.
And it's much more efficient than trying to mill it in this shape.
Right.
You need to do this, you need a 5-axis mill. If you were going to mill it
Right.
already round,
Yeah. No, thank you.
it's going to be very hard.
Right.
Milling it while it's like this is much, much easier.
Yeah. I can imagine.
Milling it while it's flat, I mean.
Right. Right.
So, in fact, that big stack, that's the starting material.
Cool. Just
So
straight
that's
raw.
just aluminum lithium plate.
Okay. So it's pretty. It's as thick as the grid is, and then you're just taking material out.
Correct.
Okay.
We actually take a thin layer off the top and the bottom,
Okay.
just to relieve some of the strain that ends up being in the material from their manufacturing process.
Okay.
Just take a thin layer off the top and bottom.
Yep.
And then mill all those pockets.
Okay. Okay.
You can.
Do you have any idea, like, how much does one of those sheets weigh like that? That looks.
I don't know that way. I mean,
It's got
it's
to be.
heavy.
It's
And
heavy.
of course, we removed 90% of that material.
Yeah, that's what I was gonna say. It probably
by
goes
the way,
from.
for GS2, we're moving to monocoque tanks. We're going to get rid of the ortho grid, because we found enough performance in other places that we don't need the performance of the orthogrid.
Really?
So if we're going to keep it for GS1, because GS1 is reusable.
Right.
So you can afford it makes more economic sense for a reusable article to go for the extra performance.
Yep.
Because that cost of doing the orthogrid gets to be amortized over 25 flights.
Yeah.
For an expendable article like GS2, the math changes.
Yep.
And since we're going to throw it away after every flight, second stage.
Yep.
We want to have. We've looked at it and we've figured out how to save. It's the mass penalty for going to monocoque is not huge.
Okay.
And the cost savings is justified.
Okay. So it's a trade. Yeah.
It's a cost versus performance trade. And we've found performance on GS2 and other places.
Cool.
For example, the BE3U engine is coming in at 172,000 pounds of thrust instead of 160.
Oh wow!
So our requirement was 160. The team did an amazing job.
Wow!
It's really turned out to be an incredible engine. I'm going to show you in a minute. So I was saying, we can switch to monocoque for GS2.
Yep.
And keep orthogrid for GS1.
Yep.
And that's a good trade.
Yeah.
Reusability, expendability.
Yep.
We're also working on a reusable second stage.
Right.
And we're going to let that be a horse race. So the goal for the expendable stage is to become so cheap to manufacture that reusability never makes sense.
Awesome.
And the goal for the reusable stage is to become so operable that expendability never makes sense. And so we'll see, because when you do that trade on paper, it just isn't obvious.
Right.
You really, it's on the first stage, it's blindingly obvious.
right. Yeah.
It's like
the bulk of the cost, the lowest velocities.
Correct.
All of
everything lines up for reusability.
Yeah.
For the second stage, it's an interesting horse race.
Yeah.
So we're just going to go barreling down both paths and try to figure out which one is better.
Really?
Yeah. Because it's just about cost.
Yeah. At the end of the day.
At the end of the day, it's just about cost.
Where are you actually at in terms of that second stage, the reusable second stage?
We're doing all the thermal. We have a design. We have, and we're doing lots of development on thermal protection systems, et cetera, et cetera.
Okay.
And that's, by the way, for a reusable second stage. There's also an interesting trade between aluminum and stainless. Mm-hmm. So because of the higher thermal properties of stainless, it's possible for it to trade better than aluminum for a reusable second stage.
Yep.
Because it gives you some benefit on re-entry.
Right.
But it doesn't give you. It's not totally obvious, because you still have thermal protection systems, and if those work correctly, there's some advantages to the aluminum, just because you can get better thermal structural mass properties with the aluminum.
Exactly. Well, the space shuttle, aluminum airframe there.
It's
exactly.
That one is a very interesting that one is an interesting trade, and you kind of have to work both. It turns into a lot of practical issues. Again, most of these interesting trades you cannot decide at the conceptual level.
Right.
Because they're happening at a much more fine-grained level. There's little details about which one is easier to manufacture,
which easier to integrate or something.
Exactly,
which
little things.
Yeah.
So you love the trades where the answer is obvious.
Yeah.
You do the trade, it's like, oh, duh. Those are great trades, and then but a lot of them unfortunately turn into, it's not clear, and the little practical issues are going to dominate. Right. Does that make sense?
And they might not rear their head until you're 3 years down the road.
They never do.
Yeah.
They're because they're at that fine level of detail.
Right. Where again, you're talking about the modeling earlier of re-entry. It's probably a similar design decision there. Like the models can get you, and the paperwork can get you so far, but to actually start doing it.
It's about the practicalities of things like thermal protection systems, and are they actually operable? How much refurbishment do you need to do, et cetera, et cetera.
Yeah, that makes sense.
So
that's cool.
We'll keep moving.
Cool.
Still have a lot to show you.
This is just as normally it's funny. I normally tell like when I go and see a rocket factory, 90% of the time I'm like, don't worry about showing me your CNC machines. Every CNC machine looks the same until you walk into a room like this and it's an entire building is one machine, and it's like
Oh, by the way,
a little different.
you should see our engine factory.
Is it
You'll have
crazy?
to go there someday. That's in Huntsville.
Yeah.
We're not going to see that today, obviously, but at another time, perhaps. But that is from a CNC point of view and machines and so on. That's incredible.
Oh, I'll bet. When you guys are ramping up BE4 production, looks like it's starting to really ramp up here.
It is. Next year we'll be building a BE4 every 3 days.
Really?
Yeah. And
Wow.
and we've already got 2 complete ship sets sitting at Vulcan, and a third ship set about to ship there too.
Wow.
And the new Glen engines are all in assembly for this first flight.
For Flight 1.
Thank you. Now we'll head to composites.
Cool.
I'm very impressed by this technology. This is a technology that would impress the Apollo engineers.
Oh, for sure.
This is, have you ever seen a big carbon fiber tape laying machine?
I just saw a decent sized one. I think it was probably 2 meters in diameter or something, and it was pretty incredible.
guys.
And I'd never actually been able to see one. I've seen like video of like the 787, machine and stuff like that.
Yeah, this will be kind of similar in scale to that.
That's crazy. It's mesmerizing.
It really is. Come on in. Hey,
How are you?
good, thank you.
You're doing a great job.
Aw, thank you. I
Appreciate
that.
I've been in the business 36 years, and
Really appreciate that.
I'll tell you now, Boeing, Northrop Grumman, United Technologies, I worked for all three for more than 10 years. It's the best company I ever worked for.
I appreciate that. Thank you.
Sincerely.
Thank you for taking the time to tell me that.
I will. This will be my last job.
All right.
I don't have to look anymore anywhere.
Thank you. That's so nice.
That's always good to hear.
What a sweet thing to say.
That's all. And now I'll slip him the 20 on the way out.
I know. I didn't
That's
even
awesome.
tip him. I mean, that's.
I love
That's,
that. That's a good sign.
So we build the fairings here, the big carbon composite fairings, and we build the payload adapters here.
Yeah.
This is the Escapade payload adapter.
Oh, that's
this is
awesome.
the actual flight article. This it basically distributes the loads. So the payload sits on the top of that adapter, and then it distributes the loads down to the periphery of the GS2 tank.
Yep. Because the load has to get transferred through the
It
walls.
has to get transferred through the walls of the tanks. So you have to spread that load out to
Yep.
get it to the periphery. And the Escapade is the vehicle is oversized for Escapade, but it's a very good first launch.
Yeah.
And we have to hit that Mars window
Yes.
coming right up.
Yeah, that is coming right up.
I want to go in and show you the big machine. This is the big oven. So after you manufacture the article, you have to cure it
Yes. Oh,
at temperature, and that's the big oven where we cure things. Over here, we do non-destructive testing of the article after it's finished.
Okay.
We use ultrasound to look for any imperfections.
this is going to be good to have this woman walking through here because the
Gives some scale. I know it's
like
hard
my
to-
brain did one of those things where at first I'm like, oh yeah, and then it was like, oh yeah,
It's
that's
a big oven.
That's a huge oven.
Come on in.
Thank you.
You got it? Come on in, guys. So, I'm going to take you all the way to the top because that's the best viewing area.
Jeez.
This we're building a fairing half right now, and so that is the head that lays the tape If you go down, you'll see the tape dispenser is down there, which we can see on the way out. You can peek at it. But basically that head travels in a machine-controlled, programmatically lays tape.
Yeah.
Little narrow carbon fiber tape. And it just builds up the entire, there it's starting to move. I don't know if we'll get to see it do its thing or not.
But layer by layer, just
layer by layer in a highly engineered pattern. And carbon fiber has strength in only one direction.
Yeah.
So what you do is you understand all of your loads, and then you design it so some of the carbon fiber you'll lay at a diagonal, you'll lay some of it perpendicular.
Yep.
And so, but you can lay the right amount because your loads aren't equal. So you can make a material that's not homogeneous.
Right.
It can be designed so that it takes the loads. Here, change places with me, you'll get a better view.
Oh, that's cool. So does it do a little bit of like curing as it's laying, or
That's
light?
for the glue.
Oh,
so
cool.
the tape has glue on it. So that's why it sticks.
Got it. Wow.
Isn't that incredible?
That's satisfying. That's really satisfying. And does this do is there a honeycomb structure, like an aluminum core inside the fairing, or is it pure carbon fiber?
There is a structure inside it too. Isn't that incredible?
That's insane. That's really cool. I love that stuff. I could watch. You shouldn't show me that because honestly, I'd probably just sit here and watch this all day, like just meditation almost.
It's incredible.
Oh, that's cool.
And on the same machine, we make it's very versatile. So we make the Payload adapters here on the same machine. It's just a different tool.
Cool.
It's a different tool and a different program.
Wow.
But it's just as versatile as like a CNC milling machine would be.
Yeah, it's like a CNC machine for carbon fiber almost.
Correct.
And it's additive.
Yeah, and it's very predictable. So we're doing non-destructive testing on this, and we have repair methodologies, but we don't have to use them very often because it's a very, very repeatable process.
Yeah.
That's what you're always looking for when you get to production.
Oh, right.
You need the process to be repeatable.
Yeah.
Which, by the way, is what you need when you're delivering 10 billion packages a year, too. You need a repeatable process.
Yeah, you do.
So, yeah, I promise you the Apollo guys would be impressed by this.
Oh, yeah. Oh, they would love this.
All right?
Mission prep.
Yeah, let's go to engines.
Cool.
I know you like engines.
I love
and
engines.
I know you know something about them. So this will be a treat for you, I promise.
Oh, I don't know what it is about the engines. Maybe
you love this giant thing moving. I mean, again,
incredible.
It's hard to get the scale of this.
Right. I mean,
it's just.
It is massive. Yeah.
You can see the pod.
Cool.
That's all of the various carbon tape.
Inside that.
And then you can set up another one over there and it can exchange pods.
That's crazy.
So you can keep the machine running.
Wow. Yeah, that is
And so you can see all the tape.
That's
see
cool.
all the tape coming down?
Wow, that's so satisfying. That's incredible.
These are giant objects.
Yes. What I think a lot of people don't always, so far the public has really mostly seen New Shepard and they think of a certain scale and certain size, and they're just going to be blindsided. I don't think the average person understands how big New Glenn is and how just total, orders of magnitude bigger.
I'm sure you're right.
It's crazy. But what I love about New Shepard is how you're able to prove out so many technologies, and
absolutely.
That you're actually, I think the most clever thing is that you're able to turn it into a product. So basically, use like a test bed as a valuable product too.
Exactly. And by the way, that is how business works, right? Your customers use your services, and then that gives you repetition to improve your services.
Mm-hmm.
By the way, I don't know if you noticed this, but we have 4 GS1s, 4 booster stages in process right here. Like you can see, I showed you the one, but here's another one. There's another one over there. There are 4 in process right now.
How big is the fleet hoping to be as far as?
Well, we're going to produce multiple GS1s every year.
Really?
So we're just going to keep producing GS1s. We're going to rate manufacturing. You have to have a rate.
Yeah.
You can't just say we're going to produce a certain number and then stop.
Right.
You want to make them all the time. Okay.
Oh, yeah.
Going in to see real flight hardware again.
This is the good stuff.
These are the flight BE3Us. So these are the LH2 LOX engines that will power the second stage. This is for the first mission. So these are the Escapade engines.
Wow. They're bigger than you think. You think the BE3...
And keep in mind, the vacuum nozzle isn't here yet.
Yeah, that's huge.
That gets attached because we install these, then we do a hot fire at sea level.
Yep.
And you can't have the nozzle skirt on for the sea level firing.
Yep.
Then we'll put for the actual mission, we'll put the vacuum skirts on. The vacuum skirts are gigantic. They dominate the whole engine. Vacuum
100%.
engines are always the prettiest.
Yeah, because
they have those big
huge
skirts. Yeah.
But it looks like they're. I didn't realize.
Do you mind if we come in for a minute? Look around a little bit.
We're gonna get out of your way.
No, you don't have to. Keep doing whatever you're doing. Don't let us bother you. Thank you.
Cool. It's
Thank
cool
you.
that everyone signed their names on
I
it.
signed all that. They had me sign my name. I signed over there
awesome.
too.
That's so cool.
This is BE3U without its skirt. It's a very interesting pump configuration. So it is back-to-back turbines. So the way this is an open expander.
Yep.
So a portion of the fuel flows through the thrust chamber to regeneratively cool the thrust chamber, and it picks up a lot of heat as it does that. So it has a lot of enthalpy, and then that gets routed to the turbines.
Yep.
So that hot hydrogen flows through the hydrogen pump turbine first.
Okay. Yep.
And
because
then
it requires the most.
It requires the most horsepower,
energy.
the most energy. And then after it exits the hydrogen turbine, it enters the oxide turbine.
Wow. It still has enough energy.
So basically you can see it, this is the high energy hot hydrogen gas coming in.
Yep.
And it passes through, this is the hydrogen pump up here.
Yep.
And so it passes through the hydrogen turbine, flowing in this direction down.
Okay.
And then right here is the aux turbine. This is the aux pump. And then it flows through the aux turbine. And what's very clever, it's a very clever little detail. The two turbines rotate in opposite directions.
Really?
Because efficiency really matters on these pumps. And even just a few points of efficiency is a big difference. Mm-hmm. And one of the waste products of flowing through a turbine is that your turbine exhaust, always has a little rotational component.
Yeah.
That rotational component is wasted.
Right.
So there's energy in that rotation which you wish you could capture.
Right.
But you can't, except
if you
have a second turbine and you rotate it in the opposite way, it gets to capture the waste energy of the first turbine. This can actually get you a few points of efficiency.
Wow.
So, and then what happens is after it comes through this turbine, I'm going to show you another. Remember I told you it had so many tricks in the 60s? They figured out so many interesting things. Yep. Here's one more trick. So this is the turbine exhaust. Comes out here. There's another duct that doesn't get installed in the sequence until the end.
Yep.
But this duct comes over here, and it dumps the turbine exhaust into this big manifold.
Yep.
And that turbine exhaust cools the nozzle skirt. So the question is, what are you going to do with your turbine exhaust?
Right.
And is there anything in an open cycle?
In an open cycle like this,
And so is there anything useful you can do with your turbine exhaust? And the answer is yes.
Yes.
You can use it to cool your skirt extension.
Sure, for your film cooling.
It's basically film cooling for the skirt. And so that's what this big manifold is.
Wow.
Isn't that interesting?
And so that's hydrogen coming out of there because you don't want to film cool with oxygen.
It's hydrogen.
You know?
So this will, so I'll we can see it over here. This. Okay. So this is the high pressure hydrogen
Okay. Yep.
coming out of the hydrogen pump.
Yep.
Okay. So this is the pump. The high pressure exit from the pump is here.
Okay.
It splits
Yep.
into two paths.
Yep.
This is the big path.
The
most
main-
most of the hydrogen goes this way.
Yep.
And it goes in straight into the injector.
Yep. Through the main fuel valve there.
Correct.
Yep.
This is a little bit of the hydrogen,
Mm-hmm.
high pressure hydrogen, goes in here, and it goes into the regen
The
channels.
regen channels. Yep.
So this is cooling the chamber,
Yep.
and then that's the piece that comes out. It comes out over there.
Over there.
Over there, and comes around and feeds the turbine.
And it's hot at that point.
It's hot hydrogen gas. 445 seconds of ISP.
Wow.
Um,
And that's considering that it's all things said and done. You know, it's not even closed cycle, and it's still getting 445.
it's not closed cycle.
Which is crazy.
But
I mean-
hydrogen also, because it's such a light molecule, if your exhaust gas is hydrogen, hot hydrogen all by itself actually gets a very high ISP.
Right, because it's so
So open
light and
cycles on
throwable.
hydrogen turn out also not to trade too badly.
Right, right.
Because what you're throwing over the edge, is literally just H2 molecules.
Yeah, yeah. Super, super lightweight.
And here we're even using it as a coolant. So
That's cool.
So
it's technically it is probably dual shafts.
it is
and
two
since
shafts.
They're counter rotating.
It's absolutely two shafts.
But they're
And you can't.
but
They're
in
just
line.
arranged in line.
Cool.
And they're back to back.
Yep.
So the two turbines face each other.
Okay. That's really cool.
Isn't that cool?
That's clever. I've never seen anything like that.
I don't know if an engine like this has ever flown before. You might know better than me.
I don't know if I've never seen a inline dual turbines that feed each other too. That's the cool thing. Is that you get energy just off after it's come through the hydrogen
Right.
pump. It's still enough to power
Yeah.
the oxygen pump. That's crazy.
This is a development article.
Okay.
And now we use it for basically
Like fitment tests and stuff?
fitment tests
Yeah.
and things like that. So this one has tons of development instrumentation on it.
Tons,
and so
yeah, you can see all the
it's
extra wire
and
looming and
we call
stuff.
it DFI. Do you know DFI, that acronym?
I don't know.
Development Flight Instrumentation. So
Oh,
it's just
cool.
it's like extra instrumentation used during the development phase.
Yep.
But yeah, the single shaft, ox-rich stage combustion. This is basically very much like the RD-180,
Yep.
except it's methane instead of
Yep.
kerosene.
Yep.
Very high performing cycle, and what we have is a life designed. I like a medium performing variant. When you want reusability in life,
Yeah.
I like a medium performing variant of a high performing cycle.
Because you have some margin in there.
Because you take stress off of everything. So for example, we operate just above 2,000 PSI chamber pressure because we are at the ox-rich stage combustion cycle operates at relatively modest temperatures, right? So the turbine gas doesn't have to be very hot.
Right.
So that you're taking all of your oxygen. All of your oxygen
It's-
is flowing through the turbine.
Yep.
So if you are flowing a small amount of like in a gas generator cycle, you're flowing a small amount of propellant through the turbine. And so you do need, to get efficiency, you need that gas to be pretty hot. And that high temperature, because of thermal cycling, is going to put a lot of stress on your turbine.
On the turbine. Yep. Yep.
And so in a ox-rich cycle, ox-rich stage combustion cycle, going through your turbine is all of the oxygen.
Yeah. Yep.
And so since you have so much mass flow, you don't have to make it that hot.
Yep.
So it's more like warm GOX
Right, then
going through the turbine.
and you're just adding just a splash of
It's a tiny bit of fuel.
So
And that's the
you're
pre-burner.
barely- yeah.
The pre-burner takes a tiny bit of fuel and all of the oxygen,
Yep.
and you kind of make warm GOX,
Yep.
and then that huge mass flow of warm GOX gives you enough horsepower on your turbine. Does that make sense?
Yeah, absolutely.
And so again, you get the thermal cycling on your turbine is more modest.
Yes.
And if you go to very high chamber pressures, you start to lose some of that advantage.
Yeah.
So, and for a booster stage, since we can afford to do that, because this isn't our upper stage engine.
Right. Right.
So this is our upper stage engine.
Yeah.
So this is liquid hydrogen. So this is another thing that the Apollo guys did. Is they said, we should use a hydrocarbon for the booster, and LH2 for the upper stages.
Yep.
It's because the high ISP really pays for itself on the upper stages.
Right. Yep.
You know, the F1 as an example was not a high performing engine.
Oh, right.
Less than 1,000 PSI of chamber pressure.
Right. Pretty
And
low specific impulse.
Low specific impulse. You know, this engine has 340 seconds of specific impulse.
Yeah. It will
So this is
walk all over the F1 in that regard.
And so on a booster engine, if you're a reusable booster, what you really need is reusability.
Yeah.
And so we need high ISP on the second stage,
Yep.
and we need high life on the first stage.
Yep. That's cool.
So that's
like
what that engine is optimized for. And the team has done an amazing job on it.
Holy crap. That was crazy. Okay, I know I've probably expressed this a few times, but you know, seeing pictures and video of this stuff is one thing. But then like standing around and inside of these things, it's insane. New Glen's just a lot bigger and more crazy than I even pictured. It's just different to see it up close and personal, and my mind's frazzled. That was incredible. And yeah, thank you so much to the Blue Origin team for helping put all this together, of course, and all this, I mean, giving me access like this, it's crazy. And especially thank you to Jeff Bezos for all of his time. That was very, very generous. So thank you so much. I had an amazing, amazing time. And make sure you're subscribed so you know when part 2 comes out. You're not gonna wanna miss this. And I owe a huge thank you to all my supporters. So those of you at Patreon and YouTube members and ex-subscribers, or however you're helping, even if you're just giving a thumbs up or super thanks or whatever, it all makes a huge difference and makes videos like this possible. So head on over to patreon.com/everydayastronaut. And while you're online, be sure and check out our awesome new merch, such as this F1 shirt that's part of our 1969 collection. We've got a ton of really, really cool stuff that pays homage to the 1969 Apollo era. And you know, I believe we're kind of in a new Apollo era ourselves these days. So really exciting stuff. We've got tons of cool stuff. So check it all out at everydayastronaut.com/shop. Thanks everybody. That's gonna do it for me. I'm Tim Dodd, the Everyday Astronaut, bringing space down to Earth for everyday people.